I'm Štěpán. I'm from Rossum. I'm missing the rest of the logo, but the O is there. And in case you are wondering what Rossum does, we are an intelligent document processing platform. What you can think of this is basically automating the processing of documents that are being processed in companies. So in a nutshell, imagine an invoice coming printed on a paper, and you want it to, in the end, land in the ERP system, like SAP or something like that. So you need to do quite a lot of steps in between, extract the data from probably a scanned invoice, then do some approvals, some matchings against various processes within the company, and that's where we stand. But I promised you LLMs and some DIY, so what's the agenda? I'll talk a bit about the task of data capture to give you some framing. That's just a part, just a small part in the end of the solution that we deliver, but it's the one that we are trying to train some language models for. I will take with you, or you with me, the trip down the memory lane, how we tackled this task before, so that you can see where are we coming from. And then, yes, a bit of LLM training and LLM serving. So yes, the data capture. It's pretty simple. You get the document and you want to turn it into something computer readable. So something human readable into something computer readable. Why is that? Well, the human readable document contains quite a lot of bloat. The computer doesn't care about the red lines and the box of milk and stuff like that. But it is quite nice to orient for a human to get the information out of it. And that's why humans are interchanging those documents. But if you want to work with it in ERP or another system, then obviously you want something that's quite easy, and you obviously can work with that much easier. This is, by the way, a nice scan, and as you will see, the issue is the scale. So up until now, it sounds like a simple thing. You know, if I showed you this invoice and told you I want this JSON, you would probably start thinking about, okay, I can use the text from the PDF. I can apply some regex. I can search for something like that. But what if you want to process millions of documents a month? What if there are thousands of use cases? So it's not just invoices. It can be basically anything you can think that the companies are interchanging in large volumes. And that can be like 100 document types, that can be receipts, that can be some labels on packages or flight, whatever, shipping something. Then there are languages that I can't understand, and yet I'm building a solution that is working with them. So this is quite usual Chinese form. If you zoom in, you can see this. This is like a nice design flaw. This stamp is there always, and it is crossing quite important text on the document. And it's like part of the standard, like put the stamp over the text that you want to read. It makes a hard time for the computer, but the humans can cope, I guess. And there is a bit of a Thai invoice. And then there's variable quality. Like you don't have scans, or you don't have digital documents. Yeah, you sometimes get scans or photos of something that was scrambled before, or spilled coffee over, or something like that. But the memory lane. So before LLMs, and if we remember that time, there was such time, you would approach this as an image. The document is an image, after all. We as a human, we work with it as with the image. So you use ConvNet. And this is how, okay, I get back to it. You use ConvNet. So you take the image, you apply some convolutional neural networks, and you get a segmentation. So think of like taking a highlighter and highlighting bits of the invoice. And we had two of those. They had around 10 million parameters, laughable at this time, I know. It had quite low resolution, output resolution. The input was bigger, 6 times bigger. And you would get some segmentation of characters or like proto-characters, the baselines of the text, and then you will get the highlightings of the pieces of information that you want to capture. So you can see, well, this is blurred because I wanted to anonymize it a bit, but it's still quite sensitive piece of information. But there was something like, you can guess it after all, don't you? So there's like the sender, and there's probably the address or some account information, account numbers and stuff like that. There's the total amount, and you can see it's segmented over there. So this is what the ConvNets were doing. And then there are tables. The tables actually are quite complex tasks that it is not solved to date. This table is pretty simple one. It's rather 2D. There's probably just like a small things out of ordinary, like this third line from below is overflowing a bit. But if you were approaching it at okay, so I'll keep each line as a single line of the table, you would fail there, I can guarantee. But the nice thing is that in this particular table, all of the values are filled in. But the usual case is if something is 0, just don't write it there. It's not important. If also sometimes, like you can say, okay, that's the issue, that there are the overflowing descriptions. But sometimes someone says, okay, we won't overflow. We will just print the text. We will continue into the other column, or we will just cut it out. The description won't be complete. So the issues are there, and that's just the values. You read out the values, and now you are thinking, what's what? So you look at the header of the table, and you can't understand it. I can't. Maybe you can. The only word I understand is unit. And I can say this is description. And this is some code, even with the typo. Well, it's not a typo. It seemed like one. And there will be some amounts and units. So this was tables. And much, much more. In order to read the invoice as an image, you started with ConvNets, but you then needed to turn the segmentation into bounding boxes. The images crops into text using some OCR model. Then probably classify the documents. You want to know if it is an invoice, a packing list, or something like that. And then you wanted some confidences, probably calibrated, well, scores calibrated into confidences. So you had yet another model for those. And to boost the accuracies, you made ensembles. So what you ended up with was a pipeline of something like 7 models with 15 million parameters in total. We called it a stack. And I'm not telling you all of that so that you can start your own IDP startup. But if you want to, feel free to. I'm saying that because in the end, we had 200 of those for each use case. Maybe for a particular customer, there was a stack. Also, the data set was different, for each use case, for each customer. And we retrained them monthly, because that's how you keep them, SOTA. So it wasn't fine. It was hard to maintain. We had to build quite a lot of orchestration around it. And if you do the math, we were basically maintaining something like 1,400 models, and in total like 3 billion parameters. And then you need to tackle the issues of like compatibility. If you did something like an improvement to the model architecture, nice thing would be if the next month you would roll it out, but what if it was not an improvement for this particular use case and stuff like that? You would have to keep the backward compatibility there. I don't want to talk about that, because what I want to talk about is how we entered the era of transformers. Oh yeah, transformers, that's how we called LLMs before we start calling them LLMs. So yes, you may be asking, so you prompted the LLM, right? That's how you use it. No, you don't. By the way, this is linked to yet another talk about why not the LLMs. But a short and concise form, we haven't found a reliable way to prompt the LLM to do the job that our pipeline is doing at the moment. Not the old pipeline, the new pipeline, maybe both pipelines. So how do we do it? We had a plan. And we had a plan to go from pixels to tokens, as simple as that. Because, at the time where we were developing the first solution, the language models were just not there yet, you couldn't take all the text in the picture, in the invoice, feed it into, what would it be? It would be recurrent neural net, you know. You would feed it with text, but it wouldn't keep enough of context so that it would be able to predict, because the text in the invoice is not linear. It's not something like that you can read from start to the end and you would understand what it is about. There are horizontal relations, vertical relations, maybe relations just going to the bottom of the page. There's a header, footer. You can imagine that. So, but with the new LLMs, there was a promise we could, but we had to move from the images to text. So we started with that. We basically built a full-page OCR. It doesn't matter whether we would build it or whether we would use a third-party solution. It is considered by now a solved problem. So I won't dive deep into it, but believe me, it's not a solved problem, in a sense that machines still do mistakes and you still have to account for them quite a lot of time. The simplest thing you can imagine in the invoice, 0 and O. It's like the obvious and usual problem, or BN8. And the thing is that for the usual OCR systems, there is not that much of a context that you can work with. And even if there is a context, the documents are still quite peculiar in a way that there are IDs or hashes or something like that. So it's not always that there is like a sane word or a sane number. It can be a mix of both if there is like an item code of a thing that is being delivered. It can be whatever string you can imagine. So it's quite hard to read it out. Yet you need to read it out accurately because that's what the systems are matching against. But anyway, as I said, not diving deep into full-page OCR, we looked at the transformer architecture. At the time, it was encoder and decoder. And as we said, we moved from pixels to tokens. And it was quite easy. And as I said, we didn't want it to prompt it. So we didn't need the decoder. We ditched it. And we created the discriminative decoder, which is basically a sigmoid layer after the encoder. It has a nice naming. It works nice, but it's pretty simple. So what we are doing is we are classifying the tokens on the page. It's basically the segmentation reimagined. Like you can think about it that instead of highlighting all the pixels, you are now highlighting all the words. So you are trying to ask, or you are trying to train the model to tell you, okay, this word is probably part of sender address. This word as well, this word as well, this word as well, this word as well. And there are pieces of descriptions, and there are pieces of quantities, and units of measures, and stuff like that. So that's what you are training the model to do. You need some post-processing to turn it into actual useful data points that you can use in the data capture system. But under the hood, that's all that it is. And in a way, it's not that much different from segmenting an image pixel by pixel. So in this sense, this was nice because we could use all, well, not all, but quite a lot of the knowledge that we had before. And that's the image that I had there before, and I skipped. This is how the Rossum UI looks. We developed it way back when the AI accuracy was definitely not there yet. And we understood that you can't just automate the process in a way, just send us the document and we will send you the results, because the results will contain errors. So what you want to do is find like a perfect cooperation between human and machine, that you provide them with an AI assistance during extracting the documents. And some of the documents will be extracted well, some not. They would need some corrections. And by providing them with this kind of UI, some of you can already say that what we did is we turned each user into an annotator, a dataset labeler, and quite proficient one, because they provided us with bounding boxes, with localization of the values, and the right values, because that's what they care about. So this was a nice way for us to improve the AI and for them to get the results fast. And having those data sets, it was quite easy to basically switch from classifying pixels to classifying tokens. And yes, how did we approach training the model? So what's the recipe? We looked at layout LM at the time. Layout XLM Roberta, you maybe know those names or maybe not, but those were the models that were out there at the time for processing documents of this type. We ended up with something with around 1 billion parameters. I know, it's not that large language model, but it's a language model, and it's quite large compared to what we had before. We gathered something like 10 million pages for unsupervised pre-training, so just trying to predict like the next word or just some masked words and some tasks like that in the document. And we gathered 2 million pages with curated annotations for supervised training. Also, we made the training in a way that simultaneously the model learned 50 use cases. So there were implemented as training heads, you can imagine that. But the thing is that instead of trying to fine-tune the model for each use case separately, we found a way to train it on all of these use cases at the same time, or at least on a lot of use cases at the same time. And we used Hugging Face datasets for that. Obviously, Hugging Face transformers, PyTorch Lightning, and few NVIDIA A100s or RTX 6000. And the training itself can be done in something like 10 GPU days. I hope those are just important data points for you that you can take away out of that, that those are like the technical rails that we used to get there. And yes?
Those use cases, are they predefined by you, or are they generated in a sort of stochastic way, or are you literally, you listed them and you found examples of them? How do you decide what the
yes.
are? How many of them are there?
Good question. The use cases, it's maybe too general word, it's basically the customer use cases. So we just looked into our customer base and we picked just some rather like wide range of use cases that would cover what we need to deliver. So those were either customer data sets or maybe data sets that we would create with our annotation team, but trying to cover the whole landscape of what we are processing. So yeah, what we get out of this training, we get something that we call T-LLM, which is an LLM for transactional documents. But regardless of the name, I like it. The nice thing is that it's just one model for all use cases, as opposed to 1,400 or 200 stacks. Depends how you look at it. But still, it's not just like an order of magnitude difference. It's a qualitative difference. We have one model. What we managed to maintain is that the model does no hallucinations, as opposed to what LLM usually do. Obviously, it still does mistakes, but not hallucinations. And as a bonus, we got an embedding for each word, because we are doing classification. So you can imagine that somewhere deep down in the model, you are getting some latent features for each word, and you are getting some latent features for each page. And those are really nice. Because yeah, you get quite a rich representation of the meaning of each word of each page. And this kind of like, what happened is like a framework emerged. Yes?
Okay, quick question about the tokens.
Yes.
So if you are speaking about semantic embedding of words, do I get it right that each word is a token? Or is it like each letter is a token, or do you have like subword?
Yeah, technically tokens are subwords, and we are just merging them into words because this is like the granularity at which it makes sense to extract the information. And obviously there's like a definition of a word when you are talking about a date or something like that. The word is like, it's not that simple, but yeah, words, subwords, not characters.
So
Yeah.
Quick question, because you said you have a lot of languages, and I can imagine that the tokenization for this will be kind of hard. So if you have some insights on that.
Yes, we, in the end, and it's quite fresh change, we switched, for example, to, we switched to, for Japanese and Chinese, we switched to one word per symbol. It's not that easy. Like for Chinese, it definitely makes sense. For Japanese, not that much. They use 3 alphabets. One of them is like a word per symbol. The other 2 are like maybe 2 or 3 symbols per word. So it's quite hard to do the tokenization right. So we opted for 1 word per symbol. Regarding tokenization, for other languages, it's pretty much simple. You work with subwords. What is hard is definitely right to left text. That's a headache. That's a big headache. Whenever you are trying to work with that, it's a headache even if you are just trying to work with that as an engineer, as a programmer, because if you are getting the outputs of the system, then you are getting scrambled order of what you are looking at. Okay, after that. No, okay. So this is the granularity stuff, and we got a framework. And it allowed us to come up with something like reg-like approach. We'll get to that later if you don't know what reg means. But for us, it means that we can provide a real-time assisted annotation of complex tables. What that means is that the user annotates the first row, and you get suggestion of the extraction of the rest of the table. Obviously, we had some solution before, but it was rather like geometry-based. This one is much more powerful because it works with semantics. So if there is a where you would see that, sure. Like if you can imagine that, for example, the description would be 2 rows in the second line item, the model would still get that because it has the information of the semantics. Like this all comprises description. So it's much better than the geometry stuff that just says, okay, somewhere over there, few pixels or just some pixels below is probably the same piece of information. And we get something which we call instant learning, which is the ability to work with the feedback, again, in near real time. What that means, as I said, the UI provides a way for the user to correct the mistakes of the AI. Usually, it would take some time for the next training to like use those corrections to improve the model. Having the embeddings allows us to retrieve similar documents or similar pages when predicting a page, and somewhat incorporate the correction into the next prediction. So yes, that's what the instant learning is. And this was all about LLM training for now. And I would like to move to LLM serving. The questions will be afterwards. Again, we had a plan, still having a plan. And it was simple, again. So we would have a service processing 1 document page at a time. We would scale it horizontally as the documents are coming in peak hours. And then we would have a database to store the embeddings for the retrieval. Let's start with the service. So the service, given what it has to do, is a mix of Python, some I/O, and some compute. And you can imagine it in a way that obviously you need to fetch some resources, let's say an image. Then you need to do some preprocessing, let's say resize it, then send it to a model, which will give you some segmentation that you do the OCR, whatever. Again, Python and compute back and forth. And then you compute the embeddings, and then you store the embeddings and store the results of the OCR. So it's quite a like balanced mix of Python waiting for something and then computing. And that's an issue. And the issue is that in order to serve such service, you need to satisfy all of the requirements for such service. And the compute is the hard part, because you need quite a lot of RAM, quite a lot of CPU for that. 4 CPUs, 8 Gs of RAMs per service. And most of the time, this hardware is doing nothing, waiting for the network, computing something in single thread in Python, slow. So the performance is something like 25 seconds per page. And for the overall deployment, at that time, we paid something like $800 a week. And we thought we can do better. So obviously, you think, let's use GPUs, because at this time, the thing that bothers you the most is the latency. You think, okay, we'll see what the cost would be, because obviously, getting to GPUs, the latency will drop, so maybe it will be better. Oh, I forgot to say, in peak hours, that would mean that we would spin up 120 pods, which makes something like this in cloud. That's a lot. It takes time to spin up this pod. So if there is like a lot of documents coming in, you are basically starting all those pods and paying 5 minutes for all of them to start? For nothing. They are not computing anything. The documents are piling up. It's slow. So yeah, the scale, everything is just wrong. So you can think about GPUs. You would need just a bit of CPU. You would need some, I guess, like pretty moderate amount of video RAM of the GPU to fit the model. It would give you 6 times faster predictions, or like the latency end to end. We haven't implemented it, so I can tell you how much would it cost. And you improve the throughput. But still, as you can see, you are paying much more expensive hardware than CPUs, and you are still doing basically nothing there. Actually, you are doing less than nothing there, because with GPU, the compute time shrinks. So before, the CPU would take, for example, like 30% of the whole processing of the page. But with GPU, it can be like 2% of time. So it's doing mostly nothing, and you are paying a lot. So what can you do about that? You can look around. There are solutions for serving. And one of them is NVIDIA Triton. In a nutshell, it's a container that allows you to serve a model. There's various formats you can use like ONNX or their proprietary TensorRT, which we've chosen, and I can recommend it if you manage to convert the model. That's a bit of a headache, but after that, it's fast. You can use various protocols, HTTP, gRPC. Again, we use gRPC. It's a bit faster. And again, a bit more of a headache, but not that much. And it's nice in a way that it's well behaved. It gives you Prometheus metrics, so you can observe it in the production and all of that. It's quite a major project by this time. So what it allows you to do, you separate all the slow Python, single-threaded Python, and all this waiting for the network into the service. You had more of these services, and they all are querying the same Triton server. It's easy. So what you do is you interleave the workload on the machine learning models, and it all simplifies a lot, and you save a lot of money. You get to latencies you could never imagine before. It's 12 times faster. It's 50 times. It has 50 times more throughput. So all is well. It was a great thing to do. It was rather simple because at this time we already had the code written in a way that all the calls to the models were kind of nicely separated, even on the levels of the abstraction of the code. So you can see there, like there's a model, it has a session, it calls a run for it, so you just switch it. So instead of it would be calling an ONNX predict at the local host, it just sends a request, waits for the response. So that was nice. Yes, and you can even save more if you look at time slicing. So again, if you are considering something like that, look at this. This is basically if your models are not that, well, you can basically serve more Triton servers on a single GPU, or you can serve more replicas of a model within a Triton server. Both has its benefits, something like high availability in cluster and stuff like that. But that's quite detailed. I talked about REC. So for those who don't know, REC is retrieval augmented generation. So when you're working with LLMs, it basically means that you take context into account during prediction to improve the extractions. That's all to it. But it's quite a hard task. As I said, we are not generating, we are discriminating. So we can call it that, but we don't. What we are doing is that we are indexing the embeddings of pages. And I can't tell you more than that. But I will talk about what we are using for it. So database. Database is quite simple. It stores usually scalar values like strings, ints, and floats. And you can search in it using things like it is greater than, it is less than, it is equal. But with vectors, it is much more hard because the data are bigger, way more bigger. And you may want to do stuff like similarity search. Again, for those who don't know, if you store vectors, you can imagine them in 2D. Then similarity is like the measure of how close those vectors are to each other. You can't say that one vector is, or you can say that one vector is bigger than the other, maybe given some measure or maybe whatever, but it's not that useful. if you look at the machine learning models, and if you look at the semantic embeddings they produce, by quite a lot of theory that we won't dive deep into, it holds, usually, that the similar stuff had similar embeddings. That's why you need similarity search. And that's what the vector databases are for. There are quite a lot of implementations, like really vector databases that were built for the purpose of processing vectors. You can search for VV8 or Qdrant and a bit more. And there are extensions to existing databases, which we opted for, because obviously when you're starting with a prototype, you want to use something that's easy or simple to start with. So we opted for PG Vector. And it turned out that the naive implementation, basically the one that needs to store the embeddings and then search for similar embeddings, works really well with PG Vector. Obviously, it was 2 years ago. The project was quite new, so it had its issues, but over time, it matured quite a lot. And I have to say that at this moment, we are indexing something like 25 million of like 4 kilobyte vectors, because it's floats of 1,000 numbers. We have about 1,000 partitions of this table. Each search into this space is like each query is applying some filters. So we are not searching this for similarity across all of the vectors, but usually across 10,000 to 200,000 vectors. So we are trying to find similar vectors among like this number of records. And it's fast. It's fast enough. And it's fast enough without index. Like the PG vector allows you to build indexes, but we so far didn't have the need to do so. And yes, we are running it on quite large HWS instance, but for now, up until now, it was still cheaper to use a bigger instance than try to invest into reimplementation, edit complexity, and stuff like that. And that's all. I'm 6 minutes over. So sorry for that.